dot is a semiconductor whose size is roughly on the order of a few nanometers. And that corresponds to anywhere from a few hundred atoms to tens of thousands of atoms. And in that size range, with semiconductors, you end up changing the properties from molecular properties where when you create excitations in the material, these excitations are what we call quantized. They're at very specific energy levels. And these energy levels, these excitations, get closer and closer together and begin to form the continuum that you end up seeing in the bulk material. So electrons in a quantum dot go from having the wave-like characters that is what is the hallmark of quantum mechanics to being the particles that you think about, these electrons that flow through circuits when you're talking about the bulk. So you have this evolution from wave-like properties to particle properties for the electron, and you're watching that evolve as the size of the quantum dot gets bigger and bigger. That's the basic physics. That's a really interesting physics that we study. And that's why they're called quantum dots, because they're really small. The way the medical applications evolved is that here we have a material that's roughly on the order of the size of a protein. So it fits in the biological framework. And it's got a surface that you can attach things to and target things. And so you can then think about taking these materials that can glow very brightly, and so you can track them, and then begin to attach them to areas or to biomolecules that you're interested in tracking. We've used that, for example, recently to be able to show that we can target very rare cell populations in vivo. These were precursor cells or hematopoietic precursor stem cells that are in very small numbers, and they're in niches until they develop into stem cells. And usually the way that it's done is by taking these cells and labeling them in vitro and re-injecting them into the animal models. But the act of taking them out, labeling them, and re-injecting them tends to disturb them. It creates a signaling pathway which makes them change. And so what you then study isn't what you think you're studying. So what we were able to show is, because the quantum dots are bright and they live a long time, we were able to target the cells endogenously, directly in vivo, without having to take them out. And we were able to then find a number of them in the marrow of these animal models. The process of getting to that stage took a long time, because what we had to do was to figure out how to get the surface of the particles to be covered with the equivalent of biological Teflon, so that they wouldn't stick to anything else except to what we were targeting. And that turned out to be a quite lengthy and complicated process.